It's my great pleasure to introduce Giuliamaria Menara, and her talk is on Eulerian magnitude homology.
Thank you very much. And yeah, and thank you for to the organizers for the invitation and for organizing this beautiful conference. So yeah, today I'm gonna talk about the work I did well recently, more or less during the past year of my PhD. And so the question that started this work is what kind of information about the graph is contained in magnitude homology groups of this graph. Now, I'm going to recall like definitions later, but why did we ask this question? So the idea is that magnitude homology groups are defined in such a way that a tuple of vertices of a graph is a magnitude homology cycle if the vertices of the tuple belong to some small enough structure, so to say. And so, yeah, we were like building on this observation to, yeah, figure out precisely what structure and when it's been detected. So, yeah, perfect. Today I'm going to recall the definitions of magnitude homology, and then I'm going to introduce Eulerian magnitude homology. That's like a version of magnitude homology with a stronger connection with this like subgraph structures counting. Then we're going to characterize precisely what subgraphs induce Eulerian magnitude homology cycles. And then we're going to move to random graphs, in particular to Erdős-Rényi random graphs. And we're going to first see how Betty numbers of some homology groups are behaving. And then we're going to discuss torsion for this class of random models. Okay. So let's start from standard magnitude homology. So we're going to need two ingredients. We need some free abelian groups and boundary maps connecting them. So first ingredient, we're going to define the KL magnitude chain as the free abelian group generated by k+1 tuples of vertices such that consecutive vertices are different. And if we visit in the graph the vertices of the tuple precisely in the order in which they appear, then we're gonna go through a path of length L. Okay, so let's see an example. What are we saying here? Let's consider this very simple graph and say we wanna build MC22. So now we're gonna need consecutive vertices to be different. So we have two possibilities. Either we have tuples of three vertices that go back and forth on one edge, so like 0, 1, 0, 1, 2, 1, and so on, or we're actually going across two edges. So 0, 1, 3, 1, 2, 3, and stuff like this. Okay. And what order counts. So 1, 2, 3 is different from 3, 1, 2. Right, and well, similarly, if we want to build MC12, we're looking for pairs of vertices such that the distance between these two vertices is 2. So in this case, we only have this for tuples, it's 0, 2, 0, 3, and the converse. And okay, just a quick remark, can you see the remark down here? Yeah, okay. Just a quick remark that's gonna be useful later. When K is bigger than L, then the magnitude chain is going to be trivial. And this is because, well, let's suppose here we're trying to build MC32. We're looking for tuples of 4 vertices such that they induce a path of length 2. And that's not going to be possible because we want consecutive vertices to be different. So, I mean, we're always going to go across an edge when we change vertex. And so that's, that's why the first groups we're going to find in the magnitude chains are the ones with K and L having the same value. Okay, so we have our free abelian groups. Let's move to defining the differential. So we're going to define a boundary map from the magnitude chain KL to the magnitude chain K-1L doing this. We're taking a K+1 tuple in MCKL, and we're removing one at a time the internal vertices from X1 to XK-1, and we're keeping the subtuple in the image if the length of the induced path after removing the vertex is still L, and it's going to 0 otherwise. So let's go back to our example. We built before MC22 and MC12, so let's compute the differential between these two guys. Say we're computing the differential of 0, 1, 0. So in this case, when we're removing 1, we're left with something that's not accepted by the definition because we're repeating 0, and so it's going to go to 0. If we compute the boundary of 1, 2, 3, then when we remove 2, this means that we're not requiring the path from 1 to 3 to go through vertex 2. And so this, in this case, the distance between 1 and 3 is only one edge. So this again is going to go to 0. If we compute the boundary of 0, 1, 3, well, even if we don't explicitly require the path from 0 to 3 to pass through vertex 1, still we need to visit two edges to go from 0 to 3, and so the subtuple is gonna survive in the image. Okay, so we have we can build the magnitude chain complex using these free abelian groups and boundary maps, and we can actually show that these maps are actual boundary maps if we remove vertex I and vertex J, or the converse, vertex J and the vertex I, the outcome doesn't change. And so we can define in the standard way the KL magnitude homology group. So now, okay, let's go back to our example and let's see what in our example the magnitude homology group 2 is. So this is when the observation we made earlier comes in useful, because since the magnitude chains are trivial when k is bigger than L, then MC32 was trivial, and so we have no incoming differential when we're computing magnitude homology with same value of k and L. So this is just the kernel of the boundary map, and I mean, we like these kind of groups because they're easier to compute. Okay, so when we make the computation of this kernel, the observation we make here is that the generators of magnitude homology are the permutations of the vertices of this triangle. So we have all the possible tuples here, 1, 2, 3, 1, 3, 2, and so on. And then stuff that goes back and forth on one edge. So I mean, this is a toy example, of course, but somehow magnitude homology is detecting the presence of this triangle plus some noise, plus this going back and forth on edges. And so we said, well, okay, let's try to remove this noisy information. And my advisor and myself, we define the Eulerian magnitude chain as like generated by k+1 tuples of vertices in the graph, such that all the vertices are different this time. And if we visit the tuple in the order in which the vertices appear, then we're inducing in the graph a path of length L. And well, this is a subgroup of the standard magnitude chain. So then we can keep the definitions as they were given originally. We're using the induced boundary map, and we can define Eulerian magnitude homology as with the usual definition of a homology group. Okay, and so now if we go back to our example and we compute the same groups, well, first thing, the Eulerian magnitude chains have less elements, and I mean, computationally wise, we are happy about this. And now the Eulerian magnitude homology group with k and L equal to 2 has rank precisely 6. So it's accounting precisely for the presence of this triangle. And so, right, okay, we have like this intuition that when we consider these groups, they're called diagonal groups, because I mean, if you just put them on a table indexed by K and L, then when you have K equal to L, they're going to be like the groups of the diagonal of this table. We have the feeling that magnitude homology groups of the diagonal, they're counting clicks or click-like subgraphs, and this is actually what's happening. So in the simplest case, when K and L are both equal to 2, we were able to actually provide a precise result. We're counting triangles, chordless squares, and squares with at most one diagonal. When K has any value, then I mean we weren't able to provide like a precise classification. But what you can do is you can say that the rank of the Eulerian magnitude homology group can be used to upper bound the number of K+1 clicks in the graph. And okay, so this was like a first step towards like figuring out precisely what sorry, what the Eulerian magnitude homology is detecting. And we said, okay, let's try to make this part more precise. Let's try to figure out precisely what we're counting here. And so, okay, we have two possibilities. Either we have like a simple case where there is a single tuple being a homology cycle, or there is like a more complicated case where we have a linear combination. So now, okay, let's start from the simple case and say we have this guy. So this is an element in EMC 55. So we have 6 vertices, and each one is at distance 1 from the previous. And from the definition, in order for this guy to be a homology cycle, we need that whenever we remove one of the internal vertices, the length is going to decrease. So the only way the length is decreasing if we remove x1 is if this edge is here. So now x0, 2, 3, 4, 5 has length 4. And we do the same reasoning for all the other vertices. When we remove x2, we want x0, 1, 3, 4, 5 to be of length 4, and so on. And then we don't really care about all the other edges. They don't play a role in the boundary map computation. So in the simple case, when we have a single tuple being a homology cycle, this is the structure we're counting. This like thing with all triangles. And okay, let's move to the less simple case, and let's start from the basic example of linear combination. Say we have two tuples such that the boundary of x bar minus x bar prime is 0 and is 0 in a non-trivial way. So the boundary of the tuples taken singularly, yeah, is non-zero. So, okay, we're gonna take, say this guy is bar x, and we said we want the boundary of 1x to be non-zero. So from what we saw before, we need to assume that one blue edge is not here, say this one. So now we have one possibility to build x bar prime, because when we remove x2, we are left to x0, 1, 3, 4, and we want it to cancel with the x bar prime. So we need x bar prime to be x0, 1, x2 prime, 3, 4. So then the two subtuples cancel. And then, yeah, we need to add these other two blue edges to cancel the other pieces of the differential of x bar prime. And then other edges can be here. We're not seeing them in the computation. The only edge that must not be there is x1, x3. This is just because if this edge is here, we don't see this whole structure. We see that the boundary of x bar is 0, the boundary of x bar prime is 0, and we don't see the whole subgraph. Yeah. And okay, so this is the base example of a linear combination. Now, of course, we can assume that each one of these blue edges is not here, and we can replace it with an x1 prime here, x3 prime here, and so on. So what is happening here? I mean, let's try to figure out when we have a linear combination, how big can it be? How is it behaving? And so, I mean, we could do this inductively, but we're choosing not to. So we're going to introduce a couple of definitions, and this is going to enable us to have a result stating precisely which combinations of tuples are producing Eulerian magnitude homology. So we're going to call this is the definition of a local collection of tuples. So I study here the precise definition, but so this local collection is what we were trying to build here. So here we build two tuples that have the same starting and ending point, and that agree in all vertices except one. So we're defining a local collection as a collection of tuples that have the same ending points, and such that for every element in the family, there are some other tuples, there is at least one other tuple that agree with xi in all vertices except one. So this is an example. In this case, we have a family of 5 tuples. And for example, say we take x bar 1, this is 0, 1, 5, 8. Now, in this case, there are four elements, 0, 2, 5, 8, 0, 3, 5, 8, and 0, 4, 5, 8, that agree in all vertices except this middle one. And this goes for all the other tuples. So, okay, these are the kind of thing we're looking at. And now, once we have this local collection, local family, we're defining the structure graph of this family as a graph that has one vertex for each tuple. So the vertices of this graph are the tuples of the local collection. And we have an edge between two vertices if the two tuples differ in exactly one vertex. So let's go back to the example before. So now x bar 1, 0, 1, 5, 8, we said before it agrees with x2, x3, and x4 in all vertices except this one. And so we're going to have an edge from x1 to x2, x3, and x4. And we keep on building this structure graph in this way. And now the nice thing, what we were able to prove is that cliques and circuits in the structure graph, they tell us precisely which coefficients we need to put in front of the elements of the local family to produce a homology cycle. So, oops, okay. So for example, here I added the gray edges because we need to kill something in order to have homology. So for example, here, here we have like a 4-click, and this is gonna go to 0 if the sum of all the coefficients is trivial. And here we have a 3-click, we have a triangle, and so we're gonna need the sum of the coefficients to be trivial. And like doing this for all the clicks in the structure graph and all the circuits, circuits in the structure graph, we're gonna be able to see precisely which linear combinations are giving homology. Here we have an example of a C4. For example, here x1 is 0, 1, 3, 5, and it agrees in one vertex with x2 and x4. And then x3 also agrees with x2 and x4. And in this case, we need something similar. We need that the sum of A1 and A2 is 0. Then we're going to need that the sum of A1 and A4 is 0, and so on. And what we were able to prove is that, well, not only cliques and circuits they give us information about which coefficients we need to put in order to have a homology cycle, but cliques and even circuits, they tell us precisely which homology cycles we have. Like they are every Eulerian homology cycle given by a linear combination is gonna correspond to either a clique or an even circuit in the structure graph. And so, yeah, we were quite happy about this result because we were able to characterize precisely, what kind of tuples, what linear combination of tuples were generating magnitude homology, Eulerian magnitude homology. Good questions up to this point? No, so this is just for linear combinations, because if you have a single tuple, then it was like the easy graph, the one with all the triangles. Yeah. What? So well, in this case, the single tuples, they're gonna be isolated vertices in the structure graph because they don't need anything, they don't need a local family to go to zero. So, I mean, when you look at the structure graph, I mean, if you take your whole graph G and you produce the structure graph of every possible tuple, everything, then you're going to see in the structure graph some isolated vertices, and those are going to be the single generators of homology. And then we're going to see cliques and even circuits. Those are going to be the linear combinations. And then other stuff is going to be something that doesn't produce homology. Okay. And I am going much faster than I thought, but it's okay. Right. Okay. So now we do have an understanding of what's happening, what is generating homology, and our next question was, well, okay, we want to try to see how Eulerian magnitude homology is behaving when, I mean, the graph is changing. And so our first attempt was to apply Eulerian magnitude homology to Erdős-Rényi random graphs and try to find like vanishing threshold and asymptotic estimates for the Betti numbers. Okay, so let's recall the definition. So an Erdős-Rényi random graph is a graph on n different nodes, and each edge is appearing with probability p independently from any other edge. And just for computational reasons, in our work, we didn't take p from 0 to 1. We took it to be n to the minus alpha, and the parameter alpha is ranging from 0 to infinity. Nothing is changing in practice, just a matter of the computations being nice. All right, so, how do we produce a vanishing threshold? Well, we know precisely which subgraphs in our graph G are induced by homology cycles. So we're going to count the occurrences of those graphs, right? So this is the simple one. And so how is this guy, what is looking like? So we have k plus 1 vertices, and they can appear in any combination we want. And then how many edges do we have? Well, we have the k edges given by the initial path. And then we're going to need these k minus 1 edges that are the triangle edges we need to have homology. And they will appear independently. So this is going to be just p to the 2k minus 1. And simplifying everything, we have that Eulerian magnitude homology vanishes if the parameter alpha is bigger than this quantity. Now, I imagine nobody's looking forward to the estimate of the more complicated case of the linear combination. Well, nice thing is that because the graph induced by a linear combination of tuples is a much more complicated structure, it has many edges. this vanishing threshold is going to be good enough. So if if the number of this simpler structure is vanishing, then also it is possible to show that also the number of the more complicated structures is vanishing. And so we already have our vanishing threshold result. So we know that asymptotically, almost surely, as n goes to infinity, the Eulerian magnetic homology groups on the diagonal are vanishing if the parameter alpha is bigger than this threshold. And you can think about everything here is asymptotic, so you can think about this as 1/2. Okay, nice. So now we know when we do and when we do not have homology, and we can ask so many questions at this point. One question that I thought was interesting is, what about torsion? Because so in standard magnetic homology, we know that there is torsion in some groups. So what about Eulerian magnetic homology? And so the question is, when this alpha is smaller than this quantity, so when we do have homology, is it torsion free? And okay, so now how do we try to solve this question? Because the construction of the Eulerian magnetic chain is nowhere near simplicial. And I mean, and it wasn't like a very direct process to apply techniques that were used for standard magnetic homology to Eulerian magnetic homology. So the idea here is to construct a pair of simplicial complexes. For people who are familiar with this, this is going to be the Eulerian version of the Asawa-Izumiara complex. Otherwise, it's just a simplicial complex with homology group isomorphic to some direct summands of Eulerian magnetic homology groups. And then we're going to see when these simplicial complexes are shellable. And Maria gave a very nice introductions about shellability on Wednesday. If you don't remember the definition, the thing we're using here is that if something is shellable, it is homotopy equivalent to a wedge of spheres. So when these guys are shellable, they're going to be torsion-free. And because their homology is isomorphic to Eulerian magnetic homology, that's also going to be torsion-free. That's the story. Okay, so what's the definition here? So we're gonna the first simplicial complex is gonna be this like simplicial complex of Eulerian tupoles from vertex A to vertex B, inducing a path of length smaller than L. So we're gonna have all the tuples A, X1, XTB, such that all vertices are different. And if we visit these vertices in the graph in this order, the induced length is going to be smaller than L. So now this thing is a simplicial complex. And if we take the set of Eulerian tuples from A to B, inducing a path of length smaller than L minus 1, this is also going to be a simplicial complex, and it's clearly a subcomplex of this first guy. Okay. So yeah, let's see precisely what we're talking about. Say we have this graph right here. We're taking the ending points A and B to be 0 and 4, and we're choosing L equal to 4. So now the only tuple that has from 0 to 4 with length precisely 4 is going to be 0, 1, 2, 3, 4. And then if we take all the other subtuples 0, 1, 2, 4, 0, 2, 3, 4, and so on, they're all going to have length smaller than 3 or 2. So they're all going to appear in this first complex, and they are also going to appear in the subcomplex. And this is like the simplicial complex we're talking about. So the first one, the Eulerian tuples with length smaller than 4, is the whole triangles, like the 3 vertices, the boundary, and the field triangles. And then the complex given by Eulerian tuples with length smaller than 3 is just going to be this red piece. Okay. So now the theorem, this theorem was proved by Asawa and Giuliamaria in 2016, I think, something like that, for standard magnitude homology, and it was like straightforward to adapt it to Eulerian magnitude homology. So it turns out that this pair of tuples that we built, that we're going to call the Eulerian Asawa-Giuliamaria complex from A to B, satisfies the requirement that up to some shift, the simplicial homology of this complex is isomorphic to Eulerian magnitude homology of here. Eulerian magnitude homology from A to B is just the family of tuples having endpoints A and B, right? And this is not a problem. We can like this is a direct summand of Eulerian magnitude homology, so we're just going to do that for every pair of tuples. Okay, now we have our simplicial complex, and with homology isomorphic to Eulerian magnitude homology. When is this guy shellable? So we're going to need to figure out when these two guys are shellable, and it turns out that the Eulerian Asawa-Giuliamaria complex is shellable asymptotically almost shortly in these two cases. So there are two cases that depend on the parameter L that we pick, and that also depends on the dimension of every facet. So if anybody is interested, I can provide the precise bound. So here the precise bound is a big product where we have terms that look like these two, and in every term there is the dimension of a different facet. So these two are the leading terms, and I mean, for clarity, I thought I just wrote this in the slide. So okay, we were able to like figure out when our simplicial complex is shellable. So now, yeah, when the Eulerian Asawa-Giuliamaria complex is shellable, it's going to be homotopy equivalent to a wedge of spheres. And so we also know when the Eulerian magnitude homology is going to be torsion free, right? Now, okay. So, right. What's the thing here? We have two different bounds. Remember, we started from a vanishing threshold for Eulerian magnitude homology, and we know that when this alpha, the parameter in the probability of the Erdős-Rényi graph was smaller than 1/2, we were going to have homology. And now we know that when alpha is smaller than one of these two guys, the graph is going to be torsion free. So, I mean, how do we put together these two results? Now, notice that here, so we said that there's the precise bound here is like a product containing these terms with the dimension of all the facets. So the last term is going to contain the dimension of the minimal facet. Okay. Now, if the minimal facet has dimension close to L, then all the other facets are going to have dimension close to L. And in the limit, this is going to go to 1. So we're going to have that when alpha is smaller than 1, this is torsion free. And when alpha is smaller than 1/2, we have Eulerian magnitude homology. And so the corollary here is that when the dimension of the minimal facet is close to L, then if we have non-vanishing Eulerian magnitude homology, then this is also going to be torsion free. And okay, so now we needed to include this hypothesis. And when is it true that the dimension of the minimal facet is close to L? And so I wasn't able to prove this yet, but what examples suggest is that if L, if we pick L smaller than some linear function of the diameter of the graph, then this is gonna be true. The idea here is that so the worst worst in this sense, the worst choice of L you can make is if you have a path graph on vertices and you pick L of the order of n square. And then the way you build a tuple is you start from vertex 1, then you pick n, 2, n minus 1, and so on. And the tuple is going to be Eulerian, like by this definition, because the vertices you see are going to be all different. But I mean, what you're doing, in fact, is you're going back and forth all the time across every edge. And so, yeah, you're going to have, where is it? Yeah. Here, the dimension of the face set is going to be n, because you have like the n vertices, and here you're going to have n squared. And that's like the worst possible thing you can do. Now, yeah, I didn't find a way to prove this yet, but it seems well, I mean, I tried many examples, and this is seems like the reasonable thing to do. And okay, so I was very fast, but yeah, this is all I wanted to say. Right. So the the results I presented here, they are in these two papers. This one is joined with my advisor Giusti, and in here we define Eulerian magnetic homology, and then we applied it to Erdős-Rényi random graphs and random geometric graphs. And for both models, we have a vanishing threshold and asymptotic estimates of the Betti numbers. And in here, well, this is the work about torsion, where I define the Eulerian version of the Asawa-Giuliamaria complex, and I proved the bounds for when this complex is shellable. And yeah, this is all. Thank you very much.
Thank you very much. Questions? Like being on Oprah.
Hey, thank you. Great talk. So I have a few questions, but for before the first one, do you have any intuition to why shellability would give me torsion free? Like, why does one look at shellability here?
Okay. So, you mean because it's random structure? Yeah. So, well, okay. Let's go here. Okay. Every facet. Okay, here we have only one facet, so this isn't a great example, because if you have one maximal face, then this is gonna be like homotopy equivalent to one. Yeah. The idea here is that every facet in this simplicial complex correspond to a certain tuple in the graph. So the idea to prove the result about shellability is I take two facet, and you just like take the tuples they induce, and then say, okay, the definition of shellability is that they have to intersect in the dimension -1 phase. So you need this facet to like either to share the dimension -1 vertices, or you need enough edges to be there so that you can build other facet from 1 to 2, so that you okay, let's just draw a picture, because I'm waving my hands too much. So say you have vertex 1, vertex 2, 3, and 4, and so the facet F1 is 1, 2, 3, 4. And then the other facet you select, because you select that randomly, is F2, 1, 2 prime, 3 prime 4. Okay, so now you need like either this edge to be here or this edge to be here. Because if either of these one edges is here, then you have a phase set one, I don't know, let's say this one, 2, 3 prime 4. This is F3. And so you have a sequence F1, F3, F2, such that they intersect in the right way. So the idea of the proof is to count the occurrences of these subgraphs that give the right sequence of phase sets. Okay.
Thanks. Can I have a sub question?
Yeah, sure.
But this looks like it would be the only way that this happens. I'm sorry, maybe I missed it. Is shalability necessary?
Yeah.
Okay,
Yeah.
okay.
It's
Okay, then it makes sense.
okay.
Can you maybe I missed it, but can you explain what torsion means in the Eulerian homology, or at least some intuition?
I mean, so the like geometric interpretation or graph theoretic interpretation, I don't know. I mean, I don't think maybe Luigi and Carlo know for standard magnitude homology, but I mean, it's an open question what it means for the graph if Eulerian magnitude homology has torsion. Here I mean, this is just a point of figuring out if there is one. And then if there is, yeah, I don't know what's it gonna mean. Yeah.
Could Eulerian magnitude homology see some other features if you use some other ring or a group instead of Z for the coefficients?
Nice question. Okay, the answer is I don't know. So I'm gonna say maybe you can find a way to highlight something that you're interested in, because the baseline is that you're gonna have edges. I mean, I don't think you're gonna change the substructures you're detecting; those are staying. But maybe with some restrictions on the coefficients, maybe you're able to decide, I want to detect only this or only that, or I want to, yeah, so I think it's going to be possible to do something like this, but the raw structures are going to stay the same. Yeah.
Okay. Thank you.
Any more questions? No? Well, thank to speak. Oh, sorry, Luigi.
So really funny, but have you thought about using the structure graphs to define a secondary Eulerian magnitude homology?
So yes, for a second, and then I thought it wasn't gonna be a good idea. No, so the thing is, the structure graph, it has like very simple structures, and you know kind of a priori what it's gonna look like. So so doing like magnitude homology on that, I don't know. You mean like a different thing, something
Like you associate the structure graph to a graph, and now you look at it as a new graph,
yeah.
and then you apply Euler or magnitude
Okay.
homology to it.
Yeah. Okay. Well, yeah, sure. I mean, well, this way, I mean, this is a way to detect all the clicks and circuits, yeah. Because I mean, at some point you're gonna detect those substructures. I mean, I didn't think about it this way, but you can certainly do it, yeah.
Okay, thanks.
Thank you for a very nice talk. My question is, do you think that the Euler characteristic of this homology could capture something about the graph?
Yeah, so if you compute the Euler characteristic of the magnitude homology, what you are getting is like this polynomial, and every coefficient in the polynomial is telling you how many of a certain subgraph is there in the graph. So I mean, this is definitely going to be like helpful. I mean, if you the thing is, computing a magnitude homology is like super expensive. So yeah, I was never in a situation where I had like an actually interesting graph, computed all the groups and computed the Euler characteristic. But I mean, it would be a way to completely identify the graph, because you would have like a list of how many triangles, how many squares, how many every subgraphs there are in there.
Okay, I think that was a record number of questions. So we'll thank the speaker one more time.